Hi everyone. All right, we are now moving on to the fifth section. In this part, we are going to explore a brand new method together. So what exactly did we cover in our previous sessions? In the earlier parts, we worked on the change of variables technique, we learned about trigonometric substitution, and we mastered partial fraction decomposition. Today, we are going to familiarize ourselves with a new and important technique known as the integration by parts method. Everyone, be ready. Have all your notes in front of you, pens in hand. With high concentration, we're going to start the new section. Well, there's a method that is more specific to multiplying algebraic expressions in trigonometry or algebraic expressions in logarithmic functions. We call this integration by parts method. This is a very practical, concise, and rapid method, but only if you manage to gain full mastery of it. After this, I will also introduce another complementary step-by-step approach, the table method, which is incredibly fast. Now let us look at a concise and relatively simple section together. Okay, let us see what it says. It states that we use this method for integrals involving the product of algebraic factors with trigonometric, exponential, or logarithmic functions. What does the rule actually state? It states the integral of u dv. What does this integral of u dv actually signify? It means that when we are given a particular integral to solve, we are going to divide it into two parts. One of them is u and the other is dv. Naturally, dx will be included inside dv. Now, what exactly should we take as u? For u, we typically choose a component that is quite simple to differentiate. And for dv, we select a component that is relatively easy to integrate. Let us take a moment to look at an example together. You can clearly see the integral of x multiplied by cosine x. This is essentially the product of an algebraic expression and a trigonometric expression. What are we going to do? We are going to take x as u. So dx becomes du, and we take cosine x dx as dv. You will take x as u and cosine x dx as dv. Why? Because I know the derivative of x, and I can very easily find the integral of cosine x dx. What is the integral of cosine x? The integral of cosine x dx becomes sine x. Therefore, sine x is v. So x is u, dx is du, cosine x dx is dv, v is sine x. Now I am going to substitute into the formula the integral of x cosine x dx. Now, according to the rule, we said this becomes u. And what did that become? That's x multiplied by v. And what did v become? Sine x minus the integral of v. But what exactly happened to the variable v? Sine x. And then there was du. What was that du supposed to be? Dx. Okay, so now we are left with the integral of sine x. And what exactly is the integral of sine x? Well, it is cosine x, but actually it is negative cosine x. Because there is already a negative sign in front of it, it then becomes positive cosine x. So the final result of the integral is now complete. X sine x plus cosine x. Now let's take a look at another example together. The integral of the natural logarithm of x dx, I'll take u, to be the natural logarithm of x. Why? Because taking its derivative is very easy. I need to choose a factor u whose derivative is easy. Then I'll take another factor dv whose integral is easy. Well, here we only have the natural logarithm of x and dx. If I choose the natural logarithm of x as u, then the differential is dx over x. We have dx over x, which becomes du. What is left? One dx remains. We will take that dx and set it as dv. I am going to take that dx as dv. You must be careful. Dx actually means 1 times dx. 1 dx is equal to dv. Now we integrate both sides of this equation. The integral of 1 times dx becomes x, and the integral of dv also becomes v. So x is equal to v. That's it. Our u and v values have now been found. Now what do I say next? I'm saying the integral of the natural logarithm of x dx is equal to u times v. That is x times the natural logarithm of x minus the integral of v times du. And v was x. What was du? We had written it dx over x. Well, the terms cancel each other out in the integral. In the second integral, what remains is minus the integral of dx, and the integral of dx, of course, becomes x. So the final result of the integration is uv, which means x times the natural logarithm of x minus x. It is a very straightforward method, as you can see. Let's move on to the next example, the integral of x e to the x dx. So what do I choose for u? In cases involving an algebraic and an exponential function, or an algebraic and a logarithmic function, or an algebraic and a trigonometric function, usually u is the algebraic expression. Why? Because its derivative is much simpler. If we were to take x and set it equal to u, then dx would simply become du. What do we take as v? The remaining part is e to the power of x dx. I am taking the integral of e to the power of x dx. What was the integral of e to the power of x c dx? We have discussed this in our previous lessons. Excellent. The integral of e to the power of x dx is simply e to the power of x itself, so it is e to the power of x. This value is equal to v. We were searching specifically for du and v, and we have successfully located both of them. Now, what was v equal to for our integral? X. What was v equal to? E to the power of x. After finding u and v, we now need to compute the integral of v times du, which is the integral of e to the power of x dx, and this becomes e to the power of x. So, the result of the integral became x times e to the power of x minus e to the power of x. I want you to solve the next example, the integral of x squared cosine x dx. Let me give you a hint. Let's agree to take x squared as u. Let dv be equal to cosine x dx. Let's start by finding the solution to the integral of x squared cosine x dx. Well, it is quite possible that you might have faced some degree of difficulty or a challenge when attempting to solve this specific problem. Let's go through the solution together. As we mentioned, we will take x squared as u and continue from there. So its differential, that is 2x dx, became du. I will keep this in mind. I took cosine x dx and assigned it as dv. Now I integrate both sides of this equation and the result is sine x equals v. Okay. Now let's write the formula. We said it becomes uv. So it is x squared sine x up to this point minus the integral of what? The integral of v times du. So what exactly was our v in this case? It was sine x. And what about our du? 2x dx. We have arrived at the integral of 2x sine x dx. And at this point, we still cannot directly integrate this expression again, because it is in itself the product of an algebraic factor and a trigonometric one. This means our very first integration by parts in the middle of our calculation has now transformed into yet another integration by parts problem. But that is absolutely no problem at all. Now this time, we are going to work on the integral of 2x sine x dx. I can simply take the 2 out as a coefficient. Then we will proceed to calculate the integral of x sine x dx together. And the integral of do x sine x, the 2 is a coefficient, it is not important. We had agreed to take x as u, so I will take x as u and sine x dx as dv. We integrate both sides. It becomes minus cosine x. In fact, that is v. Everything is ready now. The integral formula itself gives the answer uv. There is a coefficient of 2. Remember that. I am substituting uv minus the integral of v times du, which results in minus the integral of minus cosine x. That means the integral of minus cosine x dx is minus sine x. Minus sine x already has a negative sign in front, so it became plus sine x. Be careful, this is the answer for integral number 1. So the final answer will be x squared sine x, subtracting this integral number 1. Now let's move on to the next example. The integral of e to the power of x times sine x has become quite interesting. Up until now, we have only dealt with algebraic functions multiplied by trigonometric or exponential ones. But now an exponential function has appeared alongside a trigonometric one. Let's see how we are going to find this. All right, let's move on to our variable substitutions. I'm going to set sine x equal to u. You might say, sir, I'd prefer to take e to the power of x. Go right ahead. Try it and see if you can actually find a solution that way. But I would suggest that you take sine x and set it as u. If you take sine x as u, then we agree to differentiate both sides. So cosine x dx, that will become du. Well done. What will be left for dv? We are going to take e to the power of x dx, and we will set this equal to dv. Now, based on our prior agreement, we will proceed to integrate e to the power of x dx. After we integrate, the result is just e to the power of x itself. So v becomes e to the power of x. Let's substitute and see what we have. So what has happened with this problem up to this point? The integral of e to the power of x times sine x dex became uv. That means sine x times e to the power of x minus the integral of v times deu. That became e to the power of x cosine x dex. This right here is yet another integration by parts problem, and we will proceed to calculate this specific one using the integration by parts method. So how exactly do we do it? We set e to the power of x dx as dv, and we set cosine x as u. Just like with the previous integration by parts rules, we calculated this one. And the result for integral number 1 was e to the power of x cosine x plus the integral of e to the power of x sine x dx. This means we have returned to the integral from the original problem. There is absolutely no issue with that. I had previously labeled the integral of e to the power of x multiplied by cosine x as 1. Now take this result and substitute it for this expression into the very last line that we obtained. What will be the result? It will appear in this form. The integral from the problem statement is now equal to sine x times e to the power of x minus the linear term we obtained on the previous page. This linear term is e to the power of x cosine x plus the same integral. This type of integral is known as a recursive integral, meaning an integral that ultimately returns to the original problem statement. It is a very good thing too. Now let's see what happens if I apply that negative sign to the expression inside the parentheses. It is negative cosine x e to the power of x minus that integral. Now I will move that negative integral of e to the power of x sine x dx to the left side. So we end up with 2 times the integral of e to the power of x sine x dx equal to that expression. What steps should we take to finally get the integral? It is clear. We divide everything by 2. The result of the integral is obtained. We call these recursive integrals. When you have a trigonometric and an exponential term, the original problem always reappears in your solution. Move that integral to the left. It becomes double, then divide by 2. Okay, let's move on to another example. The integral of e to the power of 2 square root of x dx. We previously discussed the formula for the integral of e to the power of a first-degree algebraic expression. To solve this, we are going to take the exponent and set it equal to t, or u. It really does not make a difference. If I let 2 times the square root of x be t, then I will differentiate both sides of the equation. This means that dx divided by the square root of x becomes dt. On one side, if you solve for dx, it becomes square root of x times dt. So no trace of x should remain in the problem, right? According to our rule, what do? Dx became square root of x times dt. We had initially, at the beginning of the problem, set 2 times the square root of x equal to t. Okay, if 2 times the square root of x is t, then naturally the square root of x will be t over 2. Exactly, well done. Therefore, dx will be t over 2 times dt. Alright, now if we rewrite the integral, what exactly will we have? There was a t over 2, and I will put its 1/2 outside the integral. So it becomes 1/2 of the integral. Instead of e to the power of 2 times the square root of x, we substitute t for 2 times the square root of x. Then it becomes e to the power of t. And instead of dx, we decided to substitute t over 2 times dt. I moved the 1/2 constant to the front and it became t dt. Now take a look at its form. An algebraic function multiplied by an exponential function. What do we call these? We solve these using integration by parts. When we were doing integration by parts, I used to say we usually take the algebraic term as u. Now here the variable is t, so we will assign t to u. It is the exact same procedure we have followed before. So if u equals t, then du will be dt. And e to the power of t, dt becomes dv. The integral of e to the power of t, as you know, is just e to the power of t. So e to the power of t is going to be equal to v. Therefore, the result of this integral has a 1/2 coefficient in front. Please do not forget that. It becomes uv, which is t times e to the power of t minus the integral of v times du, which is e to the power of t dt. And as we said, the integral of e to the power of t dt is itself. So the integral's result became very straightforward. It is 1/2 te to the power of t minus e to the power of t, and then I will substitute 2 times the square root of x in place of t. So what happened in this problem was that we first performed a simple variable substitution. Now you might ask why I did not use u here. It is because u is typically used in integration by parts, and I did not want to mix them up. That is why I chose to use t instead. Let's consider another example, the integral of x arc sine x over the square root of 1 minus x squared dx. As I mentioned, arc sine refers to the inverse trigonometric function. So we have been given this question. I want to see if I can solve it using a substitution. Because this is an algebraic expression multiplied by an inverse trigonometric one. Not just a trigonometric term, I do not want to go for integration by parts. Instead, I can use a substitution. We said we choose a substitution in such a way that its derivative is present in the expression. So for instance, if I take the differential of 1 minus x squared, it is minus 2x dx. So what should I do with that arcsine function? Let's try a different approach. Let's assign arcsine x a variable. We can call it u, or here, for instance, I will name it t. If arcsine x is designated as t, I had previously mentioned to you that the differential of arcsine x is dx divided by the square root of 1 minus x squared. We can observe that, oh, a dx over the square root of 1 minus x squared is right there waiting for us. So dx divided by the square root of 1 minus x squared becomes dt, and arcsine x, we have named that t. But what about that x on the side? If arcsine x is designated as t, so sine t equals x, meaning arcsine is the inverse function. So in the problem statement, I will substitute sine t for x. I am going to substitute t for arcsine x. And then for dx divided by the square root of 1 minus x squared, I am going to put dt. This transforms the entire expression into a product of an algebraic function and a trigonometric function. And we also discussed this method, specifically the integration by parts method, which we have applied numerous times before. Today we said we will assign sine t as dev and t as u. We then take the differential of t and integrate sine t. And with the help of the integration by parts formulae, we find its result. You see, we wrote the integral of sine t dt. We had sine t dt as dv. Upon substituting these values, we arrive at the final answer. Since we have performed this type of integration many times before, I have not gone into further detail as the steps involved are quite straightforward. I want to give you some time to solve the next example. It is the integral of x arcsine of 1 over x dx. Yes, x arcsine of 1 over x. I want all of you to really spend some time on this problem. Each one of you should start working on it individually, try to find the most suitable variable substitution for it, figure out which method would be the best approach to solve it. Do not come back and look at the answer until you have solved it completely. Go on, give it a try, and come back soon. Well, I hope you were all able to solve it, and if you could not, that is perfectly all right. We are going to practice it together right here. Then you can pause the video and try to solve the question again. What was the question? It was about the integral of x arcsine of 1 over x dx. So I will choose my variable substitution. We said arcsine of 1 over x involves the inverse sine function. I hope you remember it because I need to take the derivative here. Let's take the differential of both sides. What is the derivative of 1 over x? Negative 1 over x squared all over the square root of 1 minus 1 over x squared times dx. So, if you look, we took its differential just once, and it became negative 1 divided by x squared, all over the square root of 1 minus 1 divided by x squared times dx. Now, if you simplify this a bit further and multiply both the numerator and the denominator by x squared, and then simplify the entire expression, it will become negative dx over x times the square root of x squared minus 1, which is the simplified form. So, I took arcsine of 1 over x as u and found its differential. Okay, what else is left in the problem? An x dx is left. I will take this x dx as dv. Now, what do I take? An integral? Its integral will be, yes, x squared divided by 2 is equal to the variable v. So let's substitute now and see what we are capable of. What was the rule? It was uv. I have u, I have v, I substituted them, minus the integral of v times dau. V was 1/2 x squared. We found and simplified dau together. Now we have 1/2 x squared, whose x cancels with that x. I will call this integral number 1. Let's go solve it. Once we have solved integral number 1, we can very easily replace it. Let's go see what the first solution was. Right, so we have it. I have already performed the simplification. For the 1/2 times the integral, it is x dx over the square root of x squared minus 1. We just need to substitute x squared minus 1. If we set here as x squared minus 1, let's keep in mind that we have now integrated the first part by parts and arrived at a new integral. Now we can consider anything else as t to solve this integral. We have no limitations. Immediately after we have chosen te, we must take its differential, right? So 2x dx becomes dt. We have x dx available in the numerator. Well, it is quite simple then. This expression becomes 1/2 dt. So it became 1/2. And because there was another 1/2 already there, I brought this out and it turned into 1/4. So, what did we get then? 1/4 of the integral of the numerator. dt over the square root of t. From this point on, it is obvious, isn't it? We write radical t as t to the power of 1/2. We move it to the numerator as t to the power of negative 1/2. We add 1 to the power, divide by the new power, and rewrite it in radical form. What was this? This was the one left on the previous page. The result of that integral is now obtained. I will put that aside with the rest. You will see the final answer. It is 1/2 x squared arcsine of 1 over x plus 1/2 square root of x squared minus 1. Okay, now I want to explain a method here, and then the integration by parts chapter will be closed. There is a specific method. It is called the table method. This particular method is incredibly fast. We can effectively use it in situations where an algebraic expression is multiplied by a trigonometric function, or when an algebraic expression is multiplied by an exponential function. Now, how exactly does this method operate? This table has two columns, one for the algebraic expression and the other for the trigonometric or exponential expression. I write the algebraic expression on the left side. I write the trigonometric or exponential expression on the right side. I then begin to take the derivative of the algebraic expression. I continue taking derivatives one after another until it eventually reaches 0. Now, you integrate the exponential or trigonometric function as many times as you differentiated the algebraic one. So we differentiate the algebraic part and integrate the trigonometric or exponential part. Okay, what do we do now? We integrate it the same number of times that we differentiated the algebraic expressions. And we begin with one positive and one negative sign. We multiply these, but in this specific order. Take a look. I multiply the first algebraic expression by the first order integral with a positive sign. We multiply that initial algebraic expression by the integral and its sign is positive. Then with a negative sign, we multiply the first derivative by the second integral. You will see the table just like the arrows I have shown. We multiply the second derivative by the third integral, always with a positive sign. This is a very quick and efficient method. Let's make it much clearer by walking through an example together. So let's take a look at an example. We want to integrate 3x squared times cosine 2x. We have an algebraic term and a trigonometric term. I will set up two columns for this. I have written the algebraic term 3x squared and the trigonometric function cosine 2x. Now I will start taking derivatives from the left-hand column until it completely vanishes. The derivative of 3x squared is 6x. The derivative of 6x is 6. And the derivative of 6 is 0. On the right side, I will now integrate the trigonometric functions as many times as I took derivatives. It is really quite simple. What is the integral of cosine 2x? Yes, it is 1/2 sine 2x. The integral of 1/2 sine 2x would be minus 1/4 cosine 2x. Yes, that is correct. Well done. And then the integral of that minus 1/4 cosine 2x comes out to be minus 1/8 sine 2x. It is all done now. I have finally reached the point where my derivative is completely 0. So what exactly do I do next? What is the very first algebraic term that you are seeing? I am multiplying positive 3x squared, taking into account the direction of the arrow by 1/2 sine 2x. Now I multiply the one below with a negative sign, following the arrow's direction. Then with a positive sign for the one below that, and it is gone. We just solved an algebraic trigonometric integral, just like that. Now let's look at another example. For this one, I will give you time to draw the table yourself. The integral of x cubed e to the power of 2x dx. This time, it is an algebraic and an exponential function. Make two columns for it. On the left side, put the x cubed terms, and on the right side, integrate the e terms. Everyone should try to do this on their own. Well, I hope everyone has used and enjoyed this method. It is much faster than before. You wrote x cubed as the algebraic column. X cubed, 3x squared, 6x, 6, 0. On the right, you integrated e to the power of 2x. It becomes scaled versions of itself. 1/2 e to the power of 2x, 1/4 e to the power of 2x, 1/8 e to the power of 2x, and 1/16 e to the power of 2x. Now we multiply them together with alternating positive and negative signs and proceed. It became x cubed multiplied by 1/2 e to the power of 2x, and we continued to write the expression one term after another. It is a very cool and appealing method. We only use it in specific cases where you need to be careful. Either an algebraic and a trigonometric function, or an algebraic and an exponential function. Integration by parts does not have many varied forms. This method is limited, but it is a good one. Remember its application. In problems where algebraic and trigonometric, or algebraic and exponential, or trigonometric and exponential functions are combined, we use integration by parts. I want you to practice this method thoroughly until our next session and become truly masterful. And don't forget, math is all you need.